Now that we have verified our control algorithm in desktop simulation, we are ready to deploy it to embedded microcontroller. If you remember, we are using TIC2000 motor control kit, and the code you generate from motor control block set is standard ACC code, which means you can target to any processor. In this case, this reference example shows how to partition the model so that FOC algorithm is packaged into a separate model, and it is separate from ADC and position sensor measurement and PWM write. So the key point here is you can generate algorithmic code that include current and speed loop control and integrate this code into your motor control application. So the benefit of taking algorithmic code is you can swap the code and pass to any other target processor. So Maxwell has offered TIC2000 hardware support package for generate embedded code. It is an add-on free hardware support package. And personally, I have experience with customers who are only interested in generating algorithmic code and they want to integrate into their existing legacy C code of their I/O drivers and serial port transmission. We also have customers like to generate the entire code, including the I/O driver blocks, for PWM output and ADC digital I/O feedback. So inside the library of TIC2000 support package, we also have many of choice for optimized blocks for generating efficient C code. So now we will see how to deploy the algorithm to TIC2000 microprocessor. We can automatically generate a code either floating or fixed point, download the model to the target and test it. Here is our model. It is exactly the same model we verified before in the simulation, and now we will generate a code from the control algorithm. So I turn on the sample time colors on. You can see how current loop running at 20 kHz and the speed loop run 10 times slower than that. Now I'm starting the process of code generation. Both algorithmic and driver code are generated. It is then compiled and downloaded on the processor. As we can see in the code generation report, all the generate code is open and accessible to us. We have generated about 4,000 lines of the C code. Now we open the host model. Notice that we have MTPA with field weakening. Control has been implemented. So we have a capability to turn on the field weakening control and start and stop motor button. And we can also command our speed, and we're also able to observe the signals of the speed feedback. Now we start the running the motor. And here's the hardware setup. Now I'm showing you how to increase the speed command from 500 RPM to 4,000 RPM. Where is the base speed? Notice that I'm showing you the system here. So if the speed reached 1 per unit, which is close to the base speed, we can see the speed tracks nicely with commanded speed. However, as we try to command to 5,000 RPM, which is beyond the base speed 4,000 RPM, you will see the speed response in the blue couldn't follow the yellow because we are not enabled field weakening control yet. And now we are checking the ID signal to verify that command and the feedback are still 0 in this case. Now I would like to enable the field weakening control. So now the ID feedback become negative. And let's see how does the speed response react above 1 per unit. So now you can see the speed response is able to tracking 1 per unit above by manipulating the ID currents reference to be negative. So another cool thing about motor control block set is you can also use processor in the loop to test capabilities from embedded coder. So what it does is in the desktop simulation, you can simulate control code running on the target and co-simulated with your motor and inverter models running in the Simulink. This is really helpful for testing the generated code on the target processor. You can also do code profiling. If you remember, we have been talking about one of the challenges of field orientation control is running at high sample rate, 50 microseconds. So it is very efficient in this case. You can see our current control loop is only take 5 microseconds, which is pretty efficient for 50 microsecond sample time. With the Simulink, you can also target to FPGA if you need faster sample rate. We have examples showing you how to automatically generate HDL from Simulink model and implement your motor control algorithm on FPGAs. To recap, we have been through the entire workflow for motor control, from sensor calibration, motor parameter estimation, plan modeling, control design, and code generation and implementation. And as you can see here, the motor control block set covers the entire end-to-end workflow. For modeling the motor and inverter, we introduced the ThinkScape Electrical to allow you to model different fidelity of your physical model. For design control algorithms, we talk about the Simulink control design to help you analyze and tuning the loop gains. Last but not the least, the embedded coder with fixed point designer toolbox allow you to generate efficient code for any target microprocessor. Hopefully with these capabilities, you can speed up your development process on the motor control application.